for your whiteboard weather fun fact of the day. And one of the questions that I've gotten more times than I can count is, what is the difference between partly sunny and partly cloudy? But it all depends on the percentage of sky cover. And here are your sky condition terms. When you hear these terms, this is basically what it means. Mostly sunny means a quarter or less of the sky is covered in clouds. Partly sunny and partly cloudy are pretty much interchangeable terms. Pretty much means a 50-50 split between clouds and sunshine. If your glass is half full, it's partly sunny. If it's half empty, it's partly cloudy. And then of course, mostly cloudy means at least 3/4 of the sky is covered in clouds. More than likely, more of our days are more mostly cloudy. So that's the breakdown of sky conditions from mostly sunny to mostly cloudy. That is your whiteboard weather fun fact of the day.
Hello. Today we're talking about how clouds form. Now, there's always moisture in the air. We call it humidity a lot of times, but it's water vapor. That's just water in its gaseous state. And it's invisible, but there's water vapor in the air always. Now, here's how a cloud forms. Once you start to have a rising parcel of air, as it rises, it cools. And as it cools, that gets down to the dew point. And once it reaches the dew point, that gaseous state of liquid will immediately change into a liquid state. It will form, it will go from a gas to a liquid. And when that happens, you get tiny, tiny drops of water. And that is what makes up a cloud. So again, the process is, as you have rising air, that parcel of air cools. As it cools, it reaches the dew point, and immediately when it reaches the dew point, the moisture in the air goes from a gas to a liquid, or in other words, goes from water vapor to a liquid to the clouds.
Hey, cool, are those supposed to be clouds? Dear Tim and Moby, what are clouds made of? From Mike. Well, real clouds aren't made of cotton. The air around us is full of water vapor. When that water vapor cools, it condenses around particles of dust and smoke to make tiny water droplets. Clouds form when millions of these water droplets gather together. Right, when it's really cold, vapor will condense into ice crystals instead of water droplets. That cloud on the left is made of water droplets. Its edges look solid, and it can be gray in color if the cloud is thick enough. The cloud on the right is made of tiny ice crystals. It has fuzzy edges, and it's almost pure white. You can tell a lot just by looking at clouds. Cumulus clouds look the most like cotton balls. They're puffy and white with flat bottoms. These stratus clouds form in layers. The fog you sometimes see in the morning is made of low stratus clouds. These feather-like cirrus clouds are made of ice crystals. They're bright white with wispy edges. Lots of times you see combinations of all these clouds in the sky. They come in all different shapes, sizes, and shades of gray. Wow, you really got into those clouds. Sure, I can definitely see the different types.
Most of the time, if we pay attention to clouds at all, it's because of their effect on our local weather. Or maybe it's because they make a sunset prettier. But what you might not know is that clouds affect us every day, even if we're staring at a clear blue sky. The clouds we see when we look out the window are important components of a complex global weather system. They play a key role in Earth's water cycle, carrying huge amounts of fresh water and dropping it as precipitation. And depending on their properties and where and when they form, clouds can have dramatic effects on our climate, influencing the locations and severity of floods and droughts, and even the temperature of our planet as a whole. So by understanding clouds, we can better predict severe storms, the global distribution of fresh water, and the course of climate change. But what exactly are clouds, and how do they form? All clouds share the same basic ingredient: water. They're made up of water droplets or ice crystals that have formed from water vapor in the atmosphere. Although you can't see it or feel it, the air around us contains water even on the clearest summer day. The main sources of this vapor are evaporation, which is the escape of water molecules from the surface of oceans, lakes, and soil, and transpiration, the release of water by plants. As the sun warms Earth's surface, heat is transferred into the atmosphere along with water vapor. The warmer the air, the more moisture it can hold. But warm air doesn't usually stay near the surface for long. Like a hot air balloon, it rises. As it does, it cools. The colder the air becomes, the less water vapor it's able to hold. If the air becomes cold enough, it reaches a state called supersaturation, which causes some of the water vapor to transition back to a liquid or solid state. Water molecules in the vapor form around tiny particles of dust, ice, sea salt, and pollution suspended in the atmosphere. These particles, called condensation nuclei, serve as the starting point for the formation of water droplets and ice crystals. With this final step repeated billions and billions of times, the water that's been in the atmosphere all along is suddenly visible. And a cloud is born. While we can now see the cloud, the individual droplets or ice crystals are tiny, which is why they remain airborne. But they can combine to form larger drops or crystals. And if they become large enough and too heavy to stay aloft, they'll fall as rain, snow, sleet, or hail back to Earth's surface, where the water in them came from originally.
Hello, I'm Jared, back with another episode I like to call Cooking with Clouds. Really simple ingredients. We need water vapor, we need dust, scientifically we can call that condensation nuclei, and we need cold air. Instead of using ice for the cold air, we're going to actually play with science and we're going to use air pressure. Drastically changing air pressure, we can play with the temperature. Changing air pressure changes the temperature. So we have a soda bottle. We have a pump that has a rubber stopper on the end, and we have rubbing alcohol. That's where our water vapor is going to come. Dust, it's in the air. We've all been there. You're sitting in the living room and sun's coming through the window and you can see all the dust flowing in the air. Dust is in the air. So we're going to coat our water bottle with some rubbing alcohol. I like to say just a splash is enough. And what you really need to do is swirl that around. I'm causing the water in that rubbing alcohol to evaporate. And all that water vapor is going into my bottle. Now, all I have to do is cap this. And once I start putting pressure on this, this stopper is going to want to pop out. So you want to hold it. You don't have to hold it. You're not putting tons of poundage of pressure into this thing. Just enough so that I can actually start raising the temperature. And as I pump, you're not going to see anything happening. Nothing. All I'm doing is increasing the pressure in the bottle. And that's actually raising the temperature. You know, pressure cookers, they cook faster because the high pressure is increasing the temperature. So I'm not going to put a ton of pressure in. The more pressure you put in and the quicker you release it, the denser the cloud. So now I pressurized it. I'm going to pop the stopper. You're going to hear it pop because that's all the air rushing in or rushing out of the bottle because I pressurized it, high to low pressure. And when I drop that pressure, the temperature is going to drop. And the cloud should form. Dust, water vapor, cold air. And I think I have a cloud. Wow. There's a lot of dust in the air. You can see it automatically just condensed and formed a cloud. What's neat about this is I can show you what happens when I repressurize the bottle. High pressure systems typically bring good weather. Take a look. That's good weather. Low pressure systems, storm fronts move in. You can see a low pressure system. I can keep going back and forth, making this cloud evaporate because I increase the temperature and making it condense. Thanks for watching.
Before there were weather satellites and sophisticated forecasting technology, clouds were the best way to predict what weather was coming. Clouds high up in the sky or no clouds at all meant fine weather, but clouds moving low in the sky or dark clouds meant rain was on its way. Common sayings even sprung up from our cloud observations, like red sky in the morning, sailor's warning, red sky at night, sailor's delight. And there are many more across time and different cultures. Today, geographers and meteorologists still rely on clouds to forecast the weather by studying how and why they form. Clouds give us important information on the temperature and amount of moisture in the atmosphere, which can help us predict weather from cloudless summer afternoons to overcast winter mornings. More than that, a map of the world's clouds tells us about today's energy flows and weather patterns. And unlocking the mysteries of clouds will help us better understand how the atmosphere is warmed. So today, we'll join countless peoples throughout history and look up at the clouds. I'm Alize Carrere, and this is Crash Course Geography. Clouds are often described with dramatic words like ethereal or ominous. They seem alive, born from the atmosphere, appearing as mysterious objects like UFOs. But clouds are also useful atmospheric data. Clouds are basically big water buckets floating in the atmosphere. They're composed of billions of so small they're invisible water droplets and ice crystals too small to form raindrops, so they stay suspended in the atmosphere. In fact, each cloud has its own anatomy, height, name, and reason for being. Kind of like an atmospheric person. Sailors of yore and scientists of today know that clouds can tell us more than whether it might rain. For example, we often see a villainous type of cloud hanging over cities called smog. A London physician first coined the word smog in 1900 to describe the combination of smoke and fog, the layer of cloud on the ground, that cast a pall over the city. Smog is pollution that harms our lungs, irritates our eyes and throat, and even corrodes structures over long periods of time. It also traps extra heat in the atmosphere, contributing to human-caused global warming. But the presence or absence of clouds can make a big difference in the amount of energy that reaches the surface of the Earth, too. Let's go to the thought bubble to meet them. As modern storm chasers, we're ready to drive for hours to document unique cloud formations and send data back to local meteorologists. We have to know who we're dealing with, but luckily, the vast majority of clouds are classified into 3 types, based on the way they look. The first clouds we spot are wispy tendrils of white. These cirrus clouds, or mare's tails, are made up of ice crystals, and they only exist way high up above 6,000 meters. Cirrus clouds like these reflect 50% of insolation, or incoming solar radiation. But they're even better at trapping long-wave radiation trying to move back out to space, insulating and warming the Earth's atmosphere as part of the natural greenhouse effect. Miles down the road, the sky is filled with dull, gray, flat, horizontal layers of low-level clouds below 2,000 meters. Stratus clouds like these reflect and scatter about 90% of insolation, which cools the Earth by keeping incoming energy from reaching the ground. You can blame them for the dreary weather. We keep driving as the weather clears, but now we notice lumpy cumulus clouds taking over the sky. Cumulus clouds are signs the energy in the atmosphere is shifting around. Because they can be so thick and reach so far high up into the atmosphere, they generally reflect as much energy away from the Earth as they absorb to warm the Earth. So they're basically neutral in terms of warming the atmosphere. If we're lucky driving through this hot afternoon, we'll see the bright lumpy cumulus clouds keep growing higher and thicker. Now the rain is picking up and we've found our storm. The rain, or nimbus, form of cumulus clouds. Cumulonimbus clouds are towering rain clouds which showcase a powerhouse of energy exploding as big storms. Thanks, Thought Bubble. To climate scientists, understanding clouds and how energy flows through them is critical to understanding how our Earth warms and cools, and how climates change. While cirrus clouds only appear at high levels, stratus and cumulus clouds can appear at any level. And cloud names actually describe this. So just like people can be complex, we could have, say, lumpy cumulus clouds growing in the middle above 2,000 meters but below 6,000 meters at the alto level. These are called altocumulus. Or we could have horizontal stratus clouds way high above 6,000 meters, forming icy cirrostratus layers. Cirrus, or the prefix cirro, means high level, alto refers to the mid-level, and low-level clouds are just plain stratus or cumulus. Maybe with a nimbus tacked on if it's raining. But no matter where or what they are, clouds naturally cool and heat the lower atmosphere, though how much depends on the altitude, cloud type, amount of cloud cover, and thickness. Basically, if we imagine clouds as floating water buckets, each type holds different amounts of water. And clouds are just one phase of the hydrological cycle that circulates water between the atmosphere, the hydrosphere, the lithosphere, and the biosphere. Clouds tie the atmosphere and hydrosphere together, by the way. To form clouds, water has to enter the atmosphere through evaporation, which is when liquid water molecules absorb enough heat to become energized and break away from the surface as water vapor. The water vapor stores this extra energy as latent heat of evaporation. For a gram of liquid water to turn